So, in classical physics, guys, we see everything na nangyayari, di ba? It is very straightforward. For example, nakikita natin na yung tao, winwalk niya yung dog niya around an inclined ramp, right? So ito, malalaman natin yung exact position nila, yung exact speed on how they are walking. Pero, sa quantum mechanics naman, it is more complex than that. Mas maraming nangyayari in the microscopic level, okay? They have various states, positions, and energy levels. So with that in mind, there are many concepts which classical physics cannot explain, but quantum mechanics can. With this, alamin natin ang concepts which classical physics fail to explain. So, one concept which classical physics failed to explain is black body radiation. So, a black body is an idealized object that absorbs all incident electromagnetic radiation. Okay? Kapag hinihit ang black body, guys, it emits radiation across all wavelengths. Okay? Its intensity and peak wavelength of the emitted radiation determine siya ng kanyang temperature. Okay? So, yung concept ng black body, tinatry siyang i-explain through classical physics, okay? But it eventually resulted in the discovery of quantum mechanics. So, according to classical physics, yung energy being emitted by a black body, dapat nag-i-increase siya continuously with frequency, okay? Ang basis ng concept na ito is Rayleigh-Jeans law, okay? At low frequencies, okay, gumagana naman yung theory na yon. Pero at high frequencies, nagkaroon ng ultraviolet catastrophe. So, di ba sabi ng Rayleigh-Jeans law, yung hot objects such as a black body, it should emit infinite energy in the ultraviolet range at shorter wavelengths. Okay? Pero according to experiments, meron ka lang finite amount of energy emitted at all wavelengths, even at shorter wavelengths. Okay? So guys, paano natin ma-explain yung concept ng black body radiation? So, Planck determined that if the vibrating atoms and molecules were not allowed to take on energy, okay, pero they are instead confined to a set of equally spaced energy levels, then the predicted spectra matches the experimentally determined spectra extremely well. So sinasabi lang ni Planck dito, guys, na yung allowed energies ng isang electromagnetic oscillator in a black body are represented by N, or the energy levels. Okay? So again, yung energy ng isang black body when it emits radiation, it is quantized. Okay? It is confined in equally spaced energy levels. Now, classical physics said waves and particles were completely different. Okay? Si waves, they spread out like light. Particles naman, they are tiny solid objects gaya ng electrons. Diba sa inner chem, we discussed that Einstein who showed that light can act as a particle in the photoelectric effect. And then later on, in 1924, Louis de Broglie flipped this idea. Okay, so if light waves can act like particles, then maybe particles can act like waves. With that, he proposed the equation for the de Broglie wavelength, meaning every particle has a certain wavelength. Okay, so guys, review lang po ng ating wave-particle duality concept as brought up by Louis de Broglie. Now, the double slit experiment also explained the duality of light as a wave and a particle. So when light passes through both slits, the double slit experiment, meron nagkakaroon na interference pattern. So when we try to measure which slit the particles go through, light then acts like individual particles. And doon, nagdi-disappear ang interference pattern. Okay, so this shows a double slit experiment. As you can see here, when light passes through the two slits there, meron kang interference pattern. Ito yun, guys. Okay? Now, let's watch this video first on the concept of double slit experiment.
Hey everybody, in this video we're going to talk about interference and diffraction of waves. So on the left hand side of your screen there is an example of interference occurring. This is interference of waves in a swimming pool. And then on the right hand side of your screen there is an example of diffraction occurring. This is diffraction of waves caused by a laser beam. So we're going to start things off by talking about interference. So interference is a phenomenon that occurs when two waves interact with one another. Suppose we have two waves coming together, and suppose those two waves have overlapping crests and overlapping troughs. These types of waves are what we call in phase. They are perfectly lined up with one another. And when two waves that are in phase come together, they're going to build each other up to result in a wave that has a larger amplitude. And this type of interference is what we call constructive interference. On the flip side, if we have two waves that are coming together and the crest of one of those waves overlaps with the trough of another, these types of waves are considered to be out of phase. When two out of phase waves come together, they're going to actually cancel one another out. And this phenomenon is called destructive interference. So we've talked about interference. Now let's talk a little bit about diffraction. Diffraction is a phenomenon that occurs when a wave is passed through a slit that is comparable in size to the wavelength of the wave. So suppose we pass some waves through a slit. So these lines represent the wave crests. What's going to happen is as the waves pass through that slit, they're actually going to bend around that slit. So this is what we call diffraction. And this is very different from the way that particles behave when you pass particles through a slit. When you pass particles through a slit, they're just going to pass straight through. They're not going to diffract. They're not going to bend around that slit. Now, there's a very interesting thing that occurs that involves both interference and diffraction when you pass waves through two slits. So suppose we're passing some waves, some light waves, through two slits that are separated by a distance that is comparable to the wavelength of the light. Now when this happens, each slit is going to act like a new wave source. And ultimately what we're going to get is a pattern called an interference pattern. Okay, so again, if you shoot light through two slits and you observe the resulting image on a screen, what's going to result is this interference pattern that has alternating bright spots and dark spots. And the reason why we get a pattern of interference is because the waves are actually traveling at different distances throughout the screen. So suppose we're looking at the very center of the screen. At the very center of the screen, the two waves, again, the two new waves separated by those slits, are going to travel at equal lengths. So that's going to result in constructive interference. Those waves are combining in phase to produce a wave of larger amplitude. So that results in a bright spot. But a short distance away from that bright spot, there's going to be a dark spot because now those two waves are traveling at different distances. So when those waves travel at different distances, now they're going to be out of phase and they're going to destructively interfere. So they're not going to produce any radiation at all, resulting in a dark spot. And if you move over a short distance again, well, you're going to get another bright spot because the next distance over is one full wavelength. And so you get this pattern, this alternating interference pattern of bright spots caused by constructive interference and dark spots caused by destructive interference. And this double slit type of experiment is extremely important. It was one of the fundamental experiments in describing the behavior of electrons. So we're definitely going to revisit the double slit experiment later. I hope you found this video helpful, and as always, have a good one.
Okay, guys, so that is the concept on the double slit experiment. So again, it creates an interference pattern. It can be either a constructive interference or destructive interference. Okay. So again, guys, these interference patterns, they are governed by the superposition principle. So the superposition principle states that when two or more waves overlap, the resulting wave is the sum of the individual waves. Okay. So again, this is the constructive interference. Okay. So ang nangyayari dito, yung peaks ng waves plus peaks ng isang wave, they form a constructive interference pattern. Pero, ang peaks ng isang wave plus ang troughs ng isang wave will form a destructive interference pattern. Okay? And these actually results in either light or bright or dark bands. So for constructive interference, it forms bright bands. For destructive interference, it forms a dark band. Okay? Now let's try to solve this using the de Broglie equation. What is the velocity of an electron that has a de Broglie wavelength of 10 nanometers? So again, this is the equation for the de Broglie wavelength. Lambda is equal to h over mv. Then let's just transpose to get the velocity of an electron, which is equal to nu. So that's nu is equal to h over m lambda. That is equal to 6.626 times 10 to the negative 34 joules times second, which is the Planck's constant, guys, over 9.11 times 10 to the negative 31 kilograms, which is just the mass of an electron, multiplied by the wavelength, which is given. Okay? So kinonvert ko lang yung 10 nanometers to 10 times 10 to the negative 9 meters. Okay? So guys, tandaan, yung Planck's constant, ano nga yung number niya sa ating calculator? Tama, that's 6. Tapos, for mass naman ng electron, that's 3. Okay, so you can just use exact values, then you ma-access nyo naman sa calculator. Okay, so the answer for this is velocity of an electron is equal to 7.27 times 10 to the power 4 meters per second. Okay, so as you can see, guys, lahat ng mga units natin sa equation na to are all in SI units, so that we get the SI units for the velocity of an electron. Okay, ayan. I hope that's clear, guys. Now let's proceed. Now, let's move on to the postulates of quantum mechanics. Okay? Actually, guys, maraming references na nagdadagdag pa ng ibang postulates. Pero ito yung 6 general postulates. First is, we will discuss the wave function. Second, the Hermitian operators. Third, eigenvalues. Next, the expectation values, time-dependent Schrodinger equation, and Pauli exclusion principle. Just don't worry, because yung lumalabas sa boards usually is more on just the basic concepts on these postulates of quantum mechanics. Okay? Again, basic concepts. So, huwag tayo masyadong mag-overread on the quantum mechanics. Okay? As long as you understand the basic concepts, okay? Maganda. Okay na yan. So here, guys, what do we see? It's a basketball bouncing, right? In classical physics, we can measure exactly where the ball is at every moment, its height, how fast it's moving, and predict exactly where it will land. So we can just use Newtonian's laws of motion in finding the basketball's position, velocity, and acceleration. Now, imagine trying to find an electron. Ayan. Instead of being in one exact spot, okay, yung electron natin, it behaves more like a fuzzy cloud, which is ito. Okay? The fuzzy cloud is just a visual representation of the probability of finding the electron in a certain area. So this is what quantum mechanics is all about. Particles, gaya ng electrons, do not have precise positions. Instead, the particles exist in a range of possibilities as described by a wave function. Okay? Yeah. So, a wave function, psi, so ang tawag dito, guys, the symbol na to is psi, is a mathematical description of a quantum particle state. It contains all information about that particle, where it might be, how it's moving, and how it behaves. But the wave function is not a real physical wave. Hindi kagaya ng sound waves or water waves. Okay? The quantum wave is an abstract mathematical description. So to get the real world description of particles, such as the position of an electron or the probability of finding an electron somewhere, okay, we have to square the wave function to get a probability distribution. Okay? So yung probability distribution, it tells us that we are more likely to find the electron here than here. Okay? Again, guys, a quantum wave, it is not a real physical wave. Now, an acceptable wave function obeys the following criteria. Ayan. So number 1, a wave function must be continuous. Meaning nito, dapat smooth and continuous for all x values ang ating wave function. Okay? So for example, we have here this function, e to the power of negative x squared. This function is smooth and continuous for all x. Right? its first and second derivatives exist and are continuous everywhere. Kaya continuous siya, the wave function. Next, ang unacceptable naman na wave function is gaya nito. Tingnan nyo, may conditions siya. The wave function is equal to 1 if x is less than 0, but the wave function is equal to 0 when x is greater than or equal to 0. Okay? Bakit guys? Ano sa tingin nyo? Discontinuous na kasi ang function na ito at x is equals to 0 due to the conditions given by this function. Therefore, hindi siya differentiable at x is equals to 0. So, it violates this criteria. Number 2, single-valued and finite. So, dapat ang function na natin ay single-valued and finite. For example, for every value of x in this function, where the wave function is equal to cos x, okay? For every value of x, the wave function gives one finite value. Okay? Walang ambiguity or infinity in its output. O, ano namang example ng unacceptable? So, for example, this wave function, which is equal to 1 over x, okay, it is unacceptable. Kasi at x is equals to 0, guys, okay, magiging infinite na siya. Okay? So, it's not acceptable over a domain that includes x is equals to 0. Okay? I hope that's clear, guys. Next, punta tayo sa square integrable. Okay? So, sinasabi lang dito, when you square your wave function, okay, it must be less than infinity. Okay? So, for example, for this equation, okay, wave function is equal to 1. For this domain, x is within 0 and 1. Acceptable siya, guys, because the value is always finite. Okay? Kaya siya square integrable. Unacceptable naman ang wave function is equal to 1 for x is within negative infinity to infinity. Kasi yung area under the curve is infinite. Okay? Again, infinite kasi kailangan natin finite. Therefore, hindi siya square integrable. Lastly, okay, a wave function must be normalized. Okay? So, for example, this wave function, ae to the power of negative x squared, has a normalization constant a, which is equal to 1 over pi to the power 1/4. Okay? So, guys, ang meaning lang nito, kapag skinare ko ang wave function na ito and it totals to equal to 1, then it is a normalized function. Okay? Ang unacceptable naman nito is, for example, a wave function is equal to 1 for x domain negative infinity to infinity. Okay? Unacceptable siya kasi yung area under the curve niya again is infinite. Okay? Therefore, hindi mo siya ma-normalize all over space. Okay? Again, guys, these are the criteria which shows what an acceptable wave function is. Okay? Ayan. Now, second postulate, Hermitian operators. So, Hermitian operators in a quantum mechanical system represent measurable physical quantities with real values. Okay? So, if two operators commute, meaning AB is equal to BA, they can be measured at the same time and share wave functions where both eigenvalues are exact. So, table 1 shows this. Okay? So, basically, guys, di ba sa real physical world, meron tayong momentum, potential energy, kinetic energy, total energy. Meron tayong ganun sa quantum mechanics. Okay? And for us, we use the Hermitian operators by acting it on a wave function. So, kunwari, meron kang operator dito, ganyan. It acts on a wave function. And that results in a value, okay, let's say x, times the wave function, okay, which is just the same. Okay? So, yung x na to, guys, okay, is what we call the eigenvalue. It is the number you get when the operator acts on the wave function and returns the same wave function scaled by that number. Diba? As you can see here, nag-return ang ating wave function. Okay, so the eigenvalue, it represents a possible measurement result of a physical quantity in quantum mechanics. Again, for us to get the eigenvalue, which represents a possible measurement result of a physical quantity in quantum mechanics, we have to apply an operator on the wave function. So, for example, we have the momentum operator. It is p hat. Ito yun, okay? Next, the potential energy p, it's p hat. Okay, so for example, you can operate it on a wave function, right? Ganyan. And it will result in a certain value of eigenvalue times the same wave function. Okay. Next, we have the kinetic energy operator T hat, which is this, and the total energy Hamiltonian operator, okay, which is this one. So this is just actually, guys, in total energy operator, that's just E plus P. Later, makikita niyo, okay? Okay. Now, next postulate, we have the eigenvalues. So here we have a hat, which is your operator, psi, which is your wave function, A, which is your eigenvalue. Okay? So here, sinasabi lang dito na, when you apply an operator, such as a hat, to a wave function, and you get the same wave function multiplied by a constant, which is your eigenvalue, okay, then the wave function is what we call the eigenfunction. And the constant is the eigenvalue. Okay? Again, guys, si A, yan yung eigenvalue natin. Si psi naman, yan yung eigenfunction natin. Okay? This indicates that the particle is in a definite state na tinatawag natin na eigenstate. Okay? And any measurement of that property will always give us an eigenvalue as the result. Okay? Ito, para mas magets natin ang meaning ng eigenstate and eigenvalue. So here, kunwari nasa quantum system tayo, guys. Okay? Tapos may dalawang dice ka dyan. If you roll them, they stop on a certain side, right? Kita nyo? Nag-stop siya sa certain side na yan. And that position is what we call the eigenstate. Diba? So yung top view na yan, yan yung mga sides kung saan siya nag-stop ito. Okay? Again, that is what we call the eigenstate. Now, the eigenvalue is the number you get when the die stops. So in this case, the eigenvalue is, for this die, it's 1. For the second die, it's 5. Oh, 1 plus 5 is equal to 6. So your eigenvalue is 6. Okay? Ganun yung concept na eigenvalues. Hope that's clear. So for us to practice the concept, let's answer the sample problem. So determine if the given function is an eigenfunction when subjected to the operator. If it is, find the corresponding eigenvalue. So here, we have the wave function which is equal to sine kx. And our operator is a hat which is equal to d squared over dx squared. So ang gagawin lang natin, guys, is to find whether or not the wave function is an eigenfunction. Meaning, if nag-apply ako ng operator a hat, so wave function na ito, mababalik niya ba sa right side hand ng equation ang ating wave function? Yun yung tanong. Tapos, if the function is actually an eigenfunction, then we find the eigenvalue. So let's solve. So what I did was I operated on the wave function using a hat. Okay. So a hat is our operator, d squared over dx squared times the wave function sine kx. So basically, guys, when you operate sine kx to a hat, you just have to find the second derivative of sine kx because that is your operator. So let's solve. So the first derivative of sine kx is k cos kx, right? Because the derivative of sine x is cos. Okay, please correct this in your manual. Again, the derivative of sine kx is k cos kx. Okay, again, by chain rule, kailangan natin mahanap ang derivative ng kx, which is just equal to k. Kaya siya naging k cos kx. Next, we find the derivative of k cos kx. Okay, so the derivative of k cos kx is, so the derivative of cos kx is negative sine kx. Okay, so syempre, kailangan natin mahanap ang derivative sa loob ng cos function, which is k. That's why the answer is negative k squared sine kx. Now, let's analyze. Okay, so here again, a hat is our operator, and sine kx is our wave function. O, tingnan natin sa right side, di ba? Binalik sa atin ang wave function, which is sine kx. Again, nabalik ang ating wave function after applying it using the a hat operator. Okay? Times the eigenvalue. So your eigenvalue here is negative k squared. Okay? O, kita niyo ba, guys? Di ba? Ito yung ating sine kx. Binalik lang siya after applying it using an operator. Therefore, it's an eigenfunction. Again, magiging eigenfunction lang ang wave function kapag when you apply it an operator and the result is you still get the same wave function on the right side. Okay? Ayan. A second example, we have d squared over dx squared times cos 3x plus 5. So here, guys, d squared over dx squared is our operator and cos 3x plus 5 is our wave function. So solving, we get, okay, so basically kailangan lang natin i-operate ang wave function cos 3x plus 5 by finding its second derivative. So the first derivative of cos 3x plus 5 is just negative 3 sine 3x plus 5. The derivative of negative 3 sine 3x plus 5 is just negative 3 times 3 cos 3x plus 5, which is equal to negative 9 cos 3x plus 5. Okay? Analyzing. Okay? Again, d squared over dx squared is just our operator a hat. Psi wave function is cos 3x plus 5. And then when we look at the right-hand side, guys, kita natin na binalik sa atin ang cosine function. Binalik yung exact same wave function, which is cos 3x plus 5. Therefore, cos 3x plus 5 is a eigenfunction. Tapos, it is multiplied by a certain constant, which is negative 9. And that negative 9 is your eigenvalue. Okay? Guys, lumalabas sa board exam, pero basic lang naman yung mga lumalabas sa board exam, kaya niyong sagutan, okay? Basta gets yung concept, okay? Yan. So, let's proceed to our next postulate, expectation value. So the average value for a large number of observations for a physical property is given by the expectation value, a hat in brackets. Okay? So the expectation values are important in finding the mean location of a particle in various quantum mechanical systems. Okay, so this is what you have to take note on. Again, expectation values, ginagamit siya in finding the mean location of a particle in various quantum mechanical systems. So in general, this is the equation. Ayan. So in finding expectation value, we just get the integral of the wave function conjugate times the operator a hat times the wave function. Okay? So guys, ano bang meaning ng complex conjugate? Baka nagtataka kayo, ano yung meaning nito? Okay? So, this is what we call the complex conjugate of the psi wave function. The complex conjugate of a complex number is just the same number, but with the sign of the imaginary part flipped. So for example, yung psi nyo, okay, is equal to 3x plus 2i. Oh, ito yung imaginary mo na number I. Yung complex conjugate nyo is just 3x minus 2i. Okay? Again, this is just applicable kapag may imaginary numbers yung wave function nyo. Pero kung walang imaginary wave function, yung wave function nyo, then it's just simply psi times psi. Okay? So for example, what if, ma'am, ito hindi siya complex conjugate? Okay? For example, wala tayong imaginary number. Then, pwedeng, ganito lang siya. Okay? So, ito naman, guys, it represents a 3D system. So pwedeng x, dx, dy, dz ito. Okay? Hope it's clear. So guys, why do we get the complex conjugate kung may imaginary number? Okay? In quantum mechanics, we use the complex conjugate in calculations like probabilities and expectation values to make sure na yung makuha natin na result ay isang real number. So again, this is how you get your expectation values. Okay? Now, let's watch this short video on the expectation values.
In quantum mechanics, the expectation value is the expected value of the result or measurement of an experiment. As there are often multiple possible measurement outcomes, the expectation value can be thought of as the average of all possible results weighted by their probabilities of occurring. Note, this is not the same thing as being the most probable outcome. If we have a quantum system psi, then the expectation value is equal to the following equation, where psi is a normalized state vector and A is an operator. If A has a complete set of eigenvectors and eigenvalues, then we can express the expectation value with the following equation, where the eigenvalues AJ are all the possible measurement outcomes of the experiment, and the square of their coefficient is the probability of that outcome happening. With Qiskit, you can calculate
Okay,
expectation
so let's stop
values.
there. That's the basic concept on expectation values.
In quantum-
Okay? Now we have our next postulate in quantum mechanics, that is the time-dependent Schrödinger equation. So the Schrödinger equation is used in calculating for the wave function. It describes how the system's wave function changes with time t at position x. So this is how we write the Schrödinger equation. So h hat times the wave function xt is equal to I reduced Planck's constant, okay, times this term, okay? So ma'am, ano yung h hat dyan? That is what we call the Hamiltonian operator h hat, which describes the total energy of a particle or a system. Okay, again, Hamiltonian operator, it describes the total energy of a particle or a system. So this is the equation for the Hamiltonian operator, which is equal to negative h squared over 2m times d squared over dx squared plus dx. Okay, so again, guys, Hamiltonian operator is just the kinetic energy operator plus the potential energy operator. Okay? Ayan. Now, last postulate in quantum mechanics, we have Pauli exclusion principle. So it just says that no two identical fermions, such as electrons, can be in the same quantum state at the same time. Diba na-discuss natin to sa in-org, guys? So yung Pauli exclusion principle, we can also consider it as a postulate in quantum mechanics because no two identical fermions, such as electrons, can be in the same quantum state at the same time. Okay? Specifically for the fermions, the total wave function must be antisymmetric. Pag sinabi natin antisymmetric, nag-change dapat yung sign when the two particles are swapped. Kaya nito. Bakit ma'am? Bakit kailangang mag-change ang sign kapag yung two particles ay pinag-swap ko? Okay? Kasi guys, pag nasa same quantum state, yung dalawang electrons na yan, yung wave function magka-cancel out, which gives a zero probability of that state existing. So here is the equation for Pauli exclusion principle. Again, when we swap the position of two electrons here, okay, then the wave function changes sign. Diba? Nagkaroon ka ng negative sign sa right side. Okay? Because pinag-swap mo yung dalawang electrons. Okay? Which shows us that hindi same ang quantum state ng electron 1 and electron 2. Okay? Yan. So that is the basics of our postulates in quantum mechanics. Diba? Madali lang. Okay lang yan, guys. Okay? Ang kailangan lang natin dito ay ang basic concepts. Okay? If you have any questions, feel free to ask me. Now let's move on the properties of the wave function. So here we will discuss the probability of finding a particle, Schrödinger equation, normalization, orthogonality, and the Heisenberg uncertainty principle. Okay? Now, let's further discuss the Schrödinger equation. So the time-independent Schrödinger's equation, okay, which is this one, they are used to determine the allowed energy levels for a system and explain why electrons can only have specific energies. Yan. So this is the Schrödinger equation for a 1D system. Pag sinabi natin one-dimensional system, guys, okay, yung position lang niya is just one, which is x. Pero for a 3D system naman, our position, it is a 3D system. Therefore, okay, you have to consider the coordinates x, y, z. Okay, so guys, makikita kayo, ano tong inverted triangle na to? That is what we call the Laplacian operator or Laplacian operator. Okay? So that basically just sums up the operators d squared dx squared plus d squared dy squared and d squared dz squared. Okay? Please refer to your manual on the full equation for the Laplacian operator. So shorthand notation lang siya on the on the derivatives in terms of x, y, and z. Okay? Now, sinasabi lang dito, guys, that the time-independent Schrödinger's equation can be written using the Hamiltonian operator. So in general, this is just our Schrödinger equation. H hat times the wave function is equal to E times the wave function. Okay? Again, the Hamiltonian operator, H hat, describes the total energy of the system or a particle. Okay? And the total energy of the system is just the eigenvalue of the Hamiltonian operator. Okay? I hope it's clear, guys. Next concept. Okay, so we can actually find the probability of finding a particle. Okay, so the Born interpretation states that the probability of finding a particle is given by squaring the wave function. Okay, or in other words, the complex conjugate of the wave function times the wave function. Okay, Again, guys, kung wala namang imaginary number yung wave function mo, then this is just simply this. Okay? So how do we find the probability of finding a particle? So for a 1D system, okay, we get the value of psi squared dx, okay, which gives us the probability of finding a particle between x, for example, dito, and between x plus dx. Dx. Ayan. So sinasabi dito, you can find the particle here. Okay? Next, for a 3D system naman, we have to find the value of the square of the wave function. Okay? Which gives the probability of finding a particle in a tiny volume d. Okay? So there are two ways for a 1D system and a 3D system. Now, here are the other properties of the wave function as you can see or read in your manual, okay? So here, other concept is called normalization. So in normalization, the wave function is normalized by a constant n for us to ensure that the total probability of finding the particle between positions A and B is equal to 1, okay? I hope that's clear, guys, yung ating concept ng normalization. So basically sa normalization, okay, minsan kailangan natin hanapin ang normalization constant n. Minsan kailangan natin hanapin ang normalization constant n in order to ensure that the total probability of finding the particle between positions A and B is equal to 1. Next, okay, orthogonality. So the orthogonality of two wave functions basically indicates that the different wave functions have independent quantum numbers and no election overlap. Okay, how do you prove that two wave functions are orthogonal? So you have to find the integral times the wave function I times the wave function j, which is equal to 0. Again, dapat equal to 0 yung integral nila. Okay? So this is the condition. Okay? So kapag equal to 0 ito, the meaning yan, they have independent quantum numbers and they have no election overlap. Lastly, for Heisenberg uncertainty principle, important ito, guys, it just says that the particle's position and momentum cannot both be precisely known. Okay? So greater precision in one means less in the other. So for example, we can exactly find the particle's position. Mahanap ko siya exactly where it is, itong delta x. Okay? Which means that the probability of finding the particle's momentum, okay, or yung precision of finding the particle's momentum would be much lower, much less compared to finding the particle's position. Okay? Again, kapag mas precise ang value ng position, then less precise ang value ng momentum. Pag mas precise naman ang value ng momentum, then less precise ang value ng position. Okay? In order to satisfy this inequality based on the Heisenberg uncertainty principle. So for example, guys, let's say ito, okay, mataas yan. Okay? Let's say mataas si delta x, meaning there is a great precision in finding the position of the particle. Then dapat sobrang baba ni delta p in order to satisfy this inequality. Okay? I hope that's clear, guys. Ayan. Let's try to solve in order for us to greatly understand the concepts on the wave function. So find the normalization constant of the function f of x is equal to x on the interval 0, 1. So here, guys, we want to find a normalization constant n such that pag in-integrate mo si n, which is a normalization constant, times x squared from 0 to 1, dapat equal to 1 yan. So let's try. Again, guys, this is our condition for the normalization of a wave function. Again, in order to normalize a wave function, we have to get its integral between a and b. Okay? So that's just integral wave function times the complex conjugate of the wave function dx, which is equal to 1. So ang gusto natin again, mahanap si normalization constant n in order to ensure that this wave function f of x equal to x on this interval is equal to 1. Okay? Kaya ako naglagay ng n sa loob. Okay? So solving, so the integral of nx squared dx between 0 to 1 must be equal to 1, right? Yun yung kailangan natin in order to renormalize. So, lalabas ko lang si n. Okay? Isolate lang natin siya based on our integration rules. And then we get the integral of x squared dx. So, the integral of x squared dx is x cubed over 3. Then from 0 to 1, natin siya kukunin. Okay? So, solving, we get n squared times 1/3, which is equal to 1. O ma'am, bakit 1/3? Oh, guys, tandaan yung ating math. So, x cubed, ginawa ko dito. 1 cube minus 0 cube over 3. Kaya siya naging 1/3. Okay? So, n squared times 1/3 is equal to 1. Solving and transposing, we get n. The normalization n, constant n, is equal to square root of 3. So, basically, ito yung kailangan natin na constant in order to ensure that the wave function between 0 to 1 is equal to 1. Again, this is the normalization constant. Next, we prove the orthogonality of the following functions on the interval -1, 1. So here we have two functions, f of x and g of x. So again, this is our conditions for the orthogonality of two wave functions given. Okay? So solving, this is our equation. So f of x times g of x dx. Okay? From -1 to 1. So basically, ipaprove natin kung equal to 0 to. Okay? Mapaprove lang natin na orthogonal ang two-way functions ito if it satisfies this equation, naka-yellow. Okay? So solving, okay, we get x times dx, right? Kasi f of x is just equal to 1. So hindi ko na sinama. Pero basically, guys, ito na yun. 1 times x dx. And then we solve for the integral of x dx, that is x squared over 2. So from -1 to 1, we get, ayan, 1/2 minus -1/2, which is just equal to 0, right? Therefore, the two functions, f of x equal to 1 and g of x equal to x, is orthogonal with each other, okay? Because it satisfies this equation. Okay? I hope that's clear, guys. Again, minake sure kung, dito naman sa orthogonality, tinignan natin if when you do this, when you try to satisfy the orthogonality equation, tinitingnan natin if we get 0. Kung hindi 0 yan, guys, kunwari hindi to 0, then meaning hindi orthogonal si f of x and g of x. Pero kung equal to 0 naman siya, yung kanilang integral, then they are orthogonal with each other. Okay? Oh, guys, again, hindi ko kinuha yung complex conjugate ng isa sa kanila, right? Because wala naman tayong imaginary numbers dito. Okay? I hope that's clear, guys. Again, f of x and g of x are orthogonal on the interval -1, 1. Yeah. So, guys, I hope that's clear. Now, let's proceed to our quantum mechanical system. So, syempre, guys, yung wave functions, we can apply it on various quantum mechanical systems. So, first, we have the free particle. First quantum mechanical system is a free particle. So here we have one particle that is freely moving at x. Okay, again, this is a freely moving particle. Specifically, a free particle has 0 potential energy. Its energy is mainly kinetic and it has no quantized energy levels. Okay, and its motion is free from external forces or barriers. That's why the probability of finding a free particle is infinite. Okay, it's most probable that you will find a free particle everywhere. That's why here in this figure, it is moving everywhere. Next, for a particle in a box. Okay, so guys, makinig dito dahil ito yung usually lumalabas sa board exam. Okay, so in a one-dimensional particle in a box model, from x is equals to 0 to x is equals to L, so pwede rin from x is equals to 0 to x is equals to A, depending on books. Okay? You have 0 potential energy inside the box. Ito yung box nyo, ha? Pero infinite potential energy outside the box. Okay? Anong meaning nito? Inside the box, the particle with a mass m, it is free to move within the box, but it is perfectly confined and hindi siya pwedeng lumabas. So the infinite potential energy outside the particle in the box just ensures that there is a zero probability of finding the particle outside the box. Again, the infinite potential energy just ensures that there is a 0 probability of finding the particle outside the box. Okay? So ma'am, bakit na-define to in this way? This is to simplify calculations. Okay? And it also implies that the particle experiences no forces inside the box kasi nga pwede siyang mag-freely move around. Okay? So guys, basically, yung infinite potential natin din dito at the walls, ayan, serves as a barrier for the prevention of the particle from escaping the box. Okay? So, anong implications nito sa wave function? So, sa wave function naman, which again describes the particle's behavior, the behavior of the particle inside this box, okay, then dapat equal to 0 din yung wave function at the boundaries, at the walls, because of the infinite potential energy. Okay? So, visually, guys, okay, within the box, meron kang standing wave pattern. So parang ganito, yung nasa right figure. Okay? So yung wave functions mo are just the sine wave function. So itong mga waves na to, guys, sa right figure, okay, represents the wave function inside the box. Okay? Tapos, yung nodes naman, yung may 0 electron density, they are at the boundaries. Okay? So again, only specific sine wave functions are allowed inside the box. And each wave function represents a standing de Broglie wave with discrete energy values. As you can see here, as n increases, the wavelength shortens, and then the nodes increase and the kinetic energy also increases. Again, guys, as n increases, shorten ang wavelength, right? So particle in a box also is applied in characterizing molecules with conjugated double bonds through UV-Vis spectroscopy. Okay? Now, another quantum mechanical system. Okay? So don't worry, guys, all we have to know here is just the basic concept. So the rigid rotor model describes rotational motion without distortion, where a molecule rotates around a fixed center of mass with constant moment of inertia. Okay? So tandaan, may moment of inertia ka, di ba? Kapag meron kang rotational motion. Okay? So here, a molecule rotates around a fixed center of mass. Specifically, in diatomic molecules, okay, two fixed masses, kunwari si M1, yung maroon, and si M2, yung gray, are connected by a constant bond length, as shown here. Yung center of mass nila is yung gitna nila. Okay? And meron silang constant moment of inertia. Now, their rotation depends on their masses. and their separation. Okay, R1, R2. I hope that's clear. Now, this model is useful in determining the rotational spectra of diatomic molecules. Last quantum mechanical system model is the harmonic oscillator model. So this model is useful in the characterization of molecular functional groups and understanding of bond lengths, bond force constants, and IR spectroscopy. So here, a particle vibrates when a restoring force proportional to displacement acts on it, creating a parabolic potential energy, as you can see here. Okay. Dahil dito, yung particle, meron siyang equally spaced energy levels, meaning it can only gain or lose energy in fixed amounts. Again, guys, parabolic ang potential energy niya. Okay? And usually, nahanap ang harmonic oscillator model in particles that vibrate. Okay? As you can see here, equally spaced ang kanyang energy levels, right? As you increase the energy level, as you can see here. Now, in summary, these are our quantum mechanical systems. So for a free particle, the particle moves freely without boundaries, but for a particle in a box, the particle is confined between rigid walls at x equals to 0 and x equals to L. For the energy, there is a continuous energy spectrum for a free particle, but for a particle in a box, we have discrete quantized energy levels. Okay. Then for a free particle and a particle in a box, they have the same Schrödinger equation. Okay. Same lang sila. Pero for particle in a box naman, you have boundary conditions, right? Which is from psi 0 to psi L. Okay? Now, for the wave function, iba na yung formula. So this is for the free particle wave function. Psi k is equal to ae to the power of ikx plus be to the power of negative ikx. Then for particle in a box, guys, ito yung kailangan nyo i-memorize, especially yung sa particle in a box na wave function. Okay? Pati yung energy. Psi nx is equal to square root of 2 over L sine n pi over Lx. Okay? Again, guys, lumalabas to sa board exam. So make sure na memorize nyo ang wave function for a particle in a box as well as the energy. Okay? Next, for the energy of a free particle, it's e to the ek is equal to k squared over 2m. For particle in a box, it's just easy to memorize. That's e is equal to h squared n squared over 8ml squared. Okay? So yung L, guys, is actually length. Okay? Guys, hindi na ako magde-derive dito ng mga equations, okay, on the particle in a box or wave functions or Schrödinger equations, okay? Kasi napakahaba na nila. Okay? If you want to know more on the derivations, please feel free to message me, or kaya you can always try to find it sa mga books natin or sa YouTube videos, okay? For you to further understand the derivations behind these quantum mechanical systems. Next concept, mean location of a particle. So again, a free particle has an equal probability of being found everywhere. For a particle in a box, this is it, guys. Make sure to memorize it. So it is represented by the expectation value equal to integral of 0 to L x times the square of the wave function dx. Okay. Now, the applications for a free particle quantum mechanical system is, for example, free electrons in conductors and particle beams, whereas the particle in a box model can be found in quantum wells, nanostructures, and modeling confined systems. Lastly, we have for the rigid rotor model, again, there is a rotation of molecule with fixed bond length. Vibrate for harmonic oscillator naman, it consists of vibration with restoring force proportional to displacement. Okay? So nagva-vibrate for harmonic oscillator, for rigid rotor, nagro-rotate. For the energy in rigid rotor, it consists of discrete rotational levels. For harmonic oscillator, it consists of discrete, equally spaced vibrational levels. So ang equally spaced lang ay si harmonic oscillator. Then for the Schrödinger's equation, it is different. Okay, for rigid rotor, ito yung form niya. Then for the harmonic oscillator, here we see the this equation here, which describes the harmonic oscillator. So that's negative h squared over 2m times d squared psi over dx squared plus 1/2 kx squared psi is equal to e psi. Okay, so this is your kinetic energy, but your potential energy is equal to 1/2 kx squared is characterized by this equation. Okay. Next, for the wave function, for the rigid rotor, it consists of spherical harmonics. So guys, hindi ko na susulat dito yung specific wave function for rigid rotor because that is beyond our TOS. And for harmonic oscillator naman, it consists of Hermite polynomials with Gaussian factor. For the energy, iba din. So for EL is equal to h squared over 2IL times L plus 1 for rigid rotor. For harmonic oscillator naman, tandaan to guys, En is equal to N plus 1/2 H omega. Okay. Lastly, the mean location of a particle in a rigid rotor is not defined. For harmonic oscillator, it's equal to 0. Okay. Lastly, rigid rotor model is applied in molecular rotation spectra, and for harmonic oscillator, it is applied in molecular vibrations and IR spectra. Okay. Ayan. Now we're almost done in quantum mechanics 1. Let's have a bit of a recap. Okay, so pasalubong ulit. It describes the state and information about a quantum mechanical system. Ano kaya to, guys? Tama, that's the wave function. These are values of observables in a quantum mechanical system that are discrete and quantized. Ano kaya yun, guys? Tama, these are eigenvalues. It is done on wave functions to ensure that the probability of finding a particle between positions A and B is equal to 1. Starts with letter N, guys. Ano kaya? Tama, normalization. So in this model, particle is confined between rigid walls at x is equal to 0 and x is equal to L. Ano yan, guys? Tama, particle in a box. Lastly, this model has discrete, equally spaced vibrational levels, energy levels. Tama, the harmonic oscillator model. Ayan, very good. So done na tayo sa quantum mechanics 1. Great job, you guys. Now, let's proceed with quantum mechanics 2. Here we will just discuss briefly the motion of molecules in spectroscopy, the structures of one and many electron atoms, and a bit of introduction lang to statistical thermodynamics. So more on conceptual ulit tayo, guys. Okay? For you to review the basic concepts on these very complex topics. Again, guys, huwag tayo masyadong mag-solve ng mga quantum mechanics problems because again, we have to establish our foundations regarding these topics. Okay? G? Okay, let's G. So, first type of motion in molecules is called the translational motion. Translational motion is a linear movement of molecules through space. Hindi siya usually detect in spectroscopy. An example of this include gas diffusion and molecules moving from liquid to gas. So this is how translational motion occurs. Okay, so its movement is linear. Next, we have rotational motion. So rotational motion refers to the spinning or rotating of molecules around their center of mass. And this was described earlier, right, in the rigid rotor model. So it involves the molecule's moment of inertia and can be detected using microwave spectroscopy. Ayan. As you can see here, guys, ayan, we have a molecule rotating. Ayan. So vibrational motion demand refers to the periodic movement of atoms within a molecule. And this is mainly through the chemical bonds in a molecule. So now observe ang transitions ng vibrational atoms in the infrared range and involve modes such as stretching and bending. So the number of vibrational modes depends on the molecule structure. So here we see a molecule vibrating, okay? And vibrational motion are governed by their number of vibrational or normal modes. When you say vibrational modes, it's the mode of their vibration. So for example, for a diatomic molecule, okay, there is usually one vibrational mode. For a linear polyatomic molecule, there is 3n-5 normal modes. For non-linear polyatomic molecules, there are 3n-6 normal modes. So n refers to the number of atoms in the molecule. So for example, we have water. So water is a non-linear polyatomic molecule. Its n is equal to 3 since you have 3 atoms. So its number of normal modes is 3 times 3 minus 6, which is equal to 3. Normal modes are 3 vibrational modes for water. Okay. Now, here in the figure of the right, we see that a photon with energy equal to the gap between the vibrational energy levels, okay, results in a vibrational transition. Okay. I mean, here we also see that energy levels are equally spaced. And then we also see here that from ground state, okay, the transition occurs by going through the ground state to the first excited state. Okay, Ayun. Let's proceed. So in summary, we can detect vibrational motion through 2 types of spectroscopy. That is IR spectroscopy and Raman spectroscopy. Don't worry, guys. You will still go through this pagdating nyo ng analytical chemistry. So magkaiba sila in many ways. First, for IR, infrared spectroscopy, it involves the absorption of infrared light. Pero for Raman spectroscopy, it involves the scattering of visible light. Okay, IR spectroscopy involves the change in dipole moment during the vibration of a molecule, whereas for Raman spectroscopy, it involves a change in polarizability during vibration. Okay, so examples of IR active molecules include HCl, carbon monoxide, and NO. Okay, these are all polar molecules. Meron silang change in dipole moment that results in vibration. That's why they are detected in IR spectroscopy. Whereas for Raman spectroscopy, we have H2, N2O2, CO2, CCl4. So these are non-polar or symmetric molecules. They have changes in polarizability during vibration, which makes them Raman active. Okay. Meanwhile, IR inactive molecules include H2, N2O2. And we know, guys, that these have 0 dipole moments. For Raman spectroscopy, Raman inactive molecules are less responsive, if not easily polarizable. So the spectral features in IR spec are absorption peaks at specific IR frequency. So there you will see various absorption peaks. Meanwhile, for Raman spectroscopy, you would see frequency shifts. So we would see Stokes and anti-Stokes lines. Lastly, for the output, IR spectroscopy has an IR absorption spectrum. Well, for Raman spectroscopy, it is a Raman shift spectrum, which is used as a chemical fingerprint. Again, your Raman shift spectrum, we refer to it as the chemical fingerprint of a molecule. So to learn more about infrared spectroscopy, let's watch this video.
Fourier transform infrared spectroscopy, or FTIR, is an analytical technology used in industry and academic laboratories to understand the structure of molecules and the composition of molecular mixtures. FTIR spectroscopy uses modulated mid-infrared energy to interrogate a sample. The infrared light is absorbed at specific frequencies directly related to the atom-to-atom vibrational bond energies in the molecule. When the bond energy of the vibration and the energy of the mid-infrared light are equivalent, the bond can absorb that energy. Different bonds in a molecule vibrate at different energies, and therefore absorb different wavelengths of the IR radiation. The position or frequency and intensity of these individual absorption bands contribute to the overall spectrum, creating a characteristic fingerprint of the molecule. Since FTIR spectroscopy produces signals that are specific to the type of molecular bonds or functional groups, it is the ideal tool to measure the making and breaking of chemical bonds during a reaction. Coupling FTIR spectroscopy with attenuated total reflectance, or ATR, increases the utility of this technology by providing a means to monitor reactions in situ and in real time. Measurements via ATR-FTIR eliminate the need to manually sample the reaction for offline analysis, making it possible to determine, in real time, key reaction characteristics, such as initiation, endpoint, reactive intermediates, kinetics, and mechanistic information. FTIR spectroscopy is fundamentally a qualitative or relative measurement technology, but can also produce quantitative measurements of important reaction components. FTIR follows the Beer-Lambert law, A equals ABC, where the molar absorptivity, A, and the path length, B, are essentially fixed and therefore constant. So the absorbance that a vibrational frequency for a specific bond is directly proportional to the number of the specific bond, or concentration. Once calibrated, much like that for HPLC, each measurement by the FTIR instrument will be quantitative for the reaction components it was calibrated to measure. Now, real-time quantitative information can be obtained throughout the duration of the reaction, which can be used as control variables for conditions such as add the next reagent, cool, or heat, and even end the reaction. For more information, go to mt.com/FTIR.
Okay, so that's the basic concepts on IR spectroscopy. Don't worry, guys, you will be still able to learn more about IR spectroscopy when you get to analytical chemistry. Now let's learn more about Raman spectroscopy through this video. Please watch.
Raman spectroscopy is an analytical technology used in industry and academic laboratories to understand the structure of molecules and the composition of molecular mixtures in a liquid, slurry, paste, or solid phase. Raman is often compared with IR spectroscopy because both provide information about the structure and properties of molecules from their vibrational transitions. A key difference between Raman and infrared spectroscopy is that Raman is a scattering phenomenon, whereas infrared is an absorption technique. There are two types of scattering, Rayleigh and Raman. Rayleigh is elastic scattered energy, which means the frequency of the scattered photon is the same as the excitation photon frequency. This type of energy is non-informational to the chemical makeup of the molecule being interrogated. Raman scattering, however, is inelastic photon scattering and is highly informational to the chemical makeup. Raman scattering requires two steps to occur for a molecule to Raman scatter. This two-step process is 1. The excitation source photons excite the molecule into a virtual energy state, and 2. The molecule relaxes through a release of scattered photons to a ground state. This effect is rare, with only about 1 in 10 million scattered photons being Raman scattered. Despite the effect being weak, today's technology advancements in solid-state lasers, gratings, and CCD detectors make Raman a valuable tool for identifying and monitoring compounds in a reaction or crystallization. The scattering can be either Stokes Raman scattering, where scattered photons are at longer frequencies than the excitation photons, or anti-Stokes scattering, where frequencies are shorter than those of the excitation photons. Stokes scattering is the most common type of inelastic Raman scattering that is measured by Raman instruments today. The frequency of the Raman scattered photons is dependent upon the type of bonds, as well as different atom-to-atom bonds that the laser photons interact with. This specificity of the Raman scattered photon frequency makes it valuable for its ability to identify molecules, acting like the fingerprint of a molecule. The Raman scattering of these different chemical bonds and bond types is represented in a spectrum as a function of the Raman shift versus intensity, with the Raman shift being the shift of the Raman scattered photon frequency from the excitation frequency. The intensity of the Raman signal is directly proportional to the number of a particular chemical bond or bond type, so with calibration, Raman signals can be quantitative. Additionally, when coupling a probe to a Raman system, it is now possible to measure these bonds and their changes in real time. This is valuable to understand reaction characteristics such as kinetics, initiation, endpoint, intermediates, crystal form, molecular backbone, and mechanistic information. For more information, go to mt.com/Raman-spectroscopy.
So now that you know the basic concepts on Raman spectroscopy, now, guys, did you know Raman spectroscopy was discovered by accident on a boat trip by C.V. Raman? So si C.V. Raman, actually, tumambay lang siya sa sea, okay? He just studied how light scatters using sunlight and simple tools, okay? Because he wanted to know why the sea looked blue, okay? Now, this led to his discovery called the Raman effect, and it earned him the 1930 Nobel Prize in Physics, which is the first for an Asian scientist. So here we have the very first Raman spectrograph. Okay? It was the very first Raman spectrum ever made. Now, as you can see here, di ba kanina, we computed for the vibrational modes of water, okay? And that is because the dipole moment in the polar bonds of water changes during vibration, okay? That's why we can all say that the vibrational modes of water are IR active. So here, this is what we call the symmetric stretching, okay? Symmetric yung pag-stretch ng atoms ng molecule. And then we also have what we call asymmetric stretching, so it's not symmetric. And lastly, bending. And yung mga nakita nating mga vibrational modes kanina, guys, okay, reflects in the IR spectrum in this way. So makikita natin yung IR shifts sa IR spectrum. Okay? So for asymmetric, kaya nito, ito yung kanyang shift, followed by symmetric, and then bending. Okay? And each of them have different wave numbers. So don't worry, guys, we will discuss that further in analytical chemistry. Meanwhile, we can also find the vibrational modes of carbon dioxide. carbon dioxide. So here we have symmetric stretching to left, followed by asymmetric stretching and bending. Okay. So how can we determine the IR and Raman activity of these vibrational modes? So for the symmetric stretching in CO2, it is IR inactive, okay? Because you have zero net dipole moment, but it is Raman active due to the change in polarizability. Next, asymmetric stretching naman, it is IR active, so it can be detected in IR, okay? Because of the change in dipole moment. However, asymmetric stretching of CO2 is Raman inactive. Lastly, for bending, it is IR active, okay? Because there is also a change in dipole moment. However, it is Raman inactive, okay? So, oh guys, tandaan yung ating computation for the vibrational modes, since we know that CO2, it has 3 vibrational modes. Okay? I hope that's clear, guys. Let's proceed. Now, let's proceed in the structure of atoms. Okay, so diba sa inorganic chemistry, we have discussed electronic structure. Pero guys, in terms of quantum mechanics, we can also differentiate one electron atom and many electron atoms. So an example of a one electron atom is hydrogen, okay, because it only consists of one electron. However, many electron atoms, such as helium, have 2 or more electrons. Okay, so solving the Schrödinger equation for atoms really reveals that the allowed energy levels, wave functions, and quantum numbers that describe the electron behavior. Okay, yung on electron atoms kasi guys, we can solve it exactly. However, many electron atoms require a lot of approximations because of the electron-electron interaction. So basically, yung pag-calculate ng Schrödinger's equation for the many electron atoms are more complex because of the interactions or the repulsions between electrons in many electron atoms. For one electron, such as hydrogen, this is more simple, right? Because meron tayong one electron lang for hydrogen. So for one electron atoms, okay, these consist of hydrogen and hydrogenic atoms. When we say hydrogenic atoms, these are atoms or ions with only one valence electron. So for example, see helium plus, lithium 2 plus, O7 plus, and U91 plus. So here we have hydrogen atom. Okay. So again, guys, to understand these atoms, remember that Niels Bohr proposed a model where electrons move in circular orbits with fixed energies. Diba sinabi natin the Bohr model only worked for hydrogen atom. Okay, so the Bohr's model, it also explained the emission spectrum of hydrogen, as we discussed in org. And this led to the Rydberg equation that predicts the wavelength of light emitted. Again, this is the equation for Rydberg equation. 1 over wavelength is equal to the Rydberg's constant times 1 over 1 n1 squared minus 1 over 1 n2 squared. So again, guys, n1 is less than n2 because in the emission of light, okay, it goes from a higher energy level to a lower energy level. Okay, so basically, yung final nyo na energy level is n1. Okay. However, guys, the Bohr model is limited. Okay? To more accurately describe electron behavior, kailangan natin gamitin ang Schrödinger equation, which then treats the electron as a wave. Okay? So later, makita natin yan. Now also, here we have what we call the Bohr radius. Okay? Where in the Bohr radius, guys, we have A naught is equal to 4 pi n squared h squared E naught over E squared ME. So sinasabi lang dito, guys, that the Bohr radius is actually a given constant, okay? And again, this is only applicable to hydrogen because the Bohr model is only applicable to hydrogen atoms or hydrogenic atoms, okay? Next is the Schrödinger equation. So again, to more accurately describe the behavior of a one electron atom, we use the Schrödinger equation, okay? Here, electrons are much lighter, right? And they move faster than the nucleus. That's why we assume that the nucleus is stationary in this case, okay? So this is defined by the Born-Oppenheimer approximation. Again, because of the Born-Oppenheimer approximation, we assume that the nucleus is stationary, as you can see here. Okay, so let's look at the Schrödinger equation, guys. So ang term na ito, okay, is the Coulombic potential energy of an electron that describes the electrostatic attraction between the electron and the nucleus. Again, this is the Coulombic potential energy of an electron that describes the electrostatic attraction between the electron and nucleus. So this is the Schrödinger equation for one electron atoms. Okay, let's proceed. Now let's try to find the wavelength of light emitted when electron falls from n2 is equal to 3 to n1 is equal to 2 in a hydrogen atom. So let's use the Rydberg equation in this sample problem. So basically, guys, we just have to find lambda. Okay? So substituting, we get 1 over lambda is equal to 1.0974 times 10 to the power of 7 inverse meters, which is the Rydberg constant. Again, guys, ano nga ba ang constant ito sa calculator? It's constant 16 times 1 over 2 squared, which is n1, minus 1 over 3 squared, which is n2 is equal to 3. Okay? So this is your higher energy level, and this is your lower energy level. Solving, we get 1 over lambda is equal to 1.52 times 10 to the power of 6 inverse meters, or wavelength is equal to 6.56 times 10 to the negative 7 meters, or 656 nanometers. Okay? So guys, tandaan to because lumalabas to lagi sa board exam. Again, as I said earlier regarding the Born-Oppenheimer approximation, this approximation is due to the fact that nuclei are much heavier and moves much slower than electrons. Okay? Kaya ina-assume natin na motion ng nuclei is fixed and stationary. Kung pwede natin compare sa elephant and sa fly, di ba? Ang electron, napakabilis, pero si nucleus, it's very heavy. Okay? I hope that's clear. Now, let's proceed with the structure of many electron atoms. Okay, so the structure of many electron atoms is again more complex and cannot be exactly solved due to the repulsive interactions between the electrons. So here, for example, we have electron 1, yung red, and electron 2. And this is your nucleus, okay? So meron ka kasing interactions between electron 1 and electron 2. And you have to take that into account. So one electron, guys, syempre wala yan because you only have one electron for hydrogen and hydrogenic atoms, okay? And of course, you have to take into account the interaction of electron 1 with the nucleus and the interaction of electron 2 with the nucleus Hg. Diba? So how do we solve for that? So this is the Schrodinger's equation for many electron atom, specifically for helium atom. Okay, guys, take note of this. So this term, yung green, refers to the kinetic energy of electron. Syempre, guys, we have to take into account the kinetic energy of an electron. And then this term, yung naka-red, refers to the PE or potential energy of electrons. So guys, basically, ito kinetic energy ng electron 1, kinetic energy ng electron 2. Ito naman, potential energy ng electron 1, potential energy ng electron 2. You have to take all of that into account. And then lastly, yung naka-purple, guys, is your electron repulsion. Okay? So this is your expression for electron repulsion. Okay? So basically, guys, meron kang 2 Ke terms for the helium atom and 2 Pe terms for the helium. Okay? Because you have 2 electrons. And each of that electron will interact with your helium atom. Okay? Again, tandaan ang equation nito, guys, okay? Because pwede itong lumabas sa board exam. So guys, basically, kanina sa 1 electron atom, compare natin. Okay, balik tayo. This is your Coulombic potential. This is your Pe. Okay, and this is your Ke. Okay, your Pe here describes the electrostatic attraction between the electron and the nucleus. And as you can see here, wala tayong term for electron repulsion because nag-iisa lang ang electron for hydrogen and hydrogenic atoms. Okay, guys? I hope it's clear. Let's proceed. Okay, guys, now let's proceed to statistical thermodynamics. So actually, barely ito lumalabas sa board exam, pero kasi kasama ito sa ating TOS. That's why we have to learn the basic concepts on stat thermo. So in statistical thermodynamics, a thermodynamic system is considered an assembly of submicroscopic entities, kagaya ng atoms, molecules, and photons, in a very large number of changing quantum states. So each atom, each molecule, each photon, they have a probability of being in a particular quantum state. So here we have macrostates and microstates. So when we say macrostate, okay, it is a collection of microstates that broadly describes the thermodynamic properties of a system, okay, temperature, pressure, and volume. So for example, the macrostate is 5, okay? And how do we get 5? How do we describe 5? That is described by the 2 microstates it has, which are microstate 2,3 and microstate 1,4. Now, a microstate is a configuration of particles in a system that describes the exact position and momentum of each particle. So you can see here, the first microstate, it describes 2,3 combination. Microstate 1,4 naman, it describes a 1,4 configuration. Iba sila ng configurations, but they are still describing the same macrostate, which is 5, okay? So to further understand the statistical thermodynamics concept, here we have ice and water vapor. So ice and water vapor, they are different macrostates, right? So yung quote-unquote macrostate ni ice is ice, solid siya. Si water vapor naman, ang kanyang macrostate is quote-unquote water vapor or gas. So they each have a large number of microstates. Pero yung nature, yung arrangement, energy, spacing, and yung configuration ng microstates nila are different. Okay? Now, here are some concepts that briefly describe statistical thermodynamics. So first is partition function. It is the sum of all possible microstates of a system. So lahat ng thermodynamic properties such as the Helmholtz free energy, entropy, and heat capacity can be calculated using this function. So partition function Q or capital Q is equal to summation of e to the power of negative beta EI. Okay, so I refers to the number of microstates. So for example, ith microstate, okay, again, I refers to the microstates. Beta is equal to 1 over KBT. So KB, kappa B, okay, ito, is referred to as the Boltzmann constant. And this is a constant na mahanap nyo din sa calculator. Lastly, the Boltzmann distribution determines the probability of a system to be in a specific microstate with energy. Okay? So again, it determines the probability of a system to be in a specific microstate I. Okay? Kaya siya I dito. So Pi means the probability of a system to be in a ith microstate. And that is equal to e to the power of negative beta EI over Q. Again, EI, guys, energy in the ith microstate. Because again, a macrostate can have many microstates, okay? So to further understand the concept on partition function and Boltzmann distribution, wag kayong mag-alala, guys, we have a simple example for you. Particle can occupy 3 levels. E0 is equal to 0 electron volts, E1 is equal to 0.1 electron volts, and E2 is equal to 0.2 electron volts. So yung 0, 1, 2 na yan also refers to microstates, okay? Given that the temperature is equal to 300 Kelvin and the Boltzmann constant is 8.617 times 10 to the negative 5 electron volts over Kelvin, find the partition function and the probability of finding the particle at E1. When they say the probability of finding the particle at E1, it means the probability of finding the particle at the energy of the first microstate, okay? So first, let's find the partition function. So ito yun. Q is equal to, so ang ginawa ko guys, iniisa-isa ko yung E0, E1, and E2. Okay, so ito na yun. Q is equal to e to the power of negative beta EI over KBT. Okay, so yung ginawa ko guys, yung beta, we know that it's 1 over KBT, right? So nilagay ko na siya agad sa equation. Kaya siya ganito. Okay? Solving, we get, ayan. So this is the Boltzmann constant again, guys. Ito yung given temperature. Solving for that, we get Q is equal to 1.0212. So that is our partition function. Now we solve for the probability of finding the particle at E1. So at the first energy level or at the first microstate. So solving, substitute lang natin yung values. Okay? Again, guys, yung beta dito, ginawa na natin 1 over KBT. That's why ito na siya. Okay? Solving, we get the probability of finding the particle at E1 or at the first energy level, okay, is equal to 0.0204. Okay? Diba? Very easy lang. Don't worry guys, we only need to study the basic concepts on these. Ayan, so patapos na tayo sa ating quantum mechanics 2. Now, dito na yung aking pasalubong sa inyo. So, let's all answer together. It refers to the linear movement of molecules through space and describes the overall motion of molecules. Ano yan? Tama, that's translational motion. Next, please explain the way atoms in a molecule move or vibrate. Its number depends on the molecule. Ano nga yan, guys? Tama, vibrational modes. In this type of spectroscopy, light scatters upon striking a polarizable molecule. It creates a unique Raman spectrum or a chemical fingerprint. Raman spectroscopy, correct? It describes the neglect of the motion of the heavier and slower nucleus in solving the Schrödinger equation. Anong tawag sa approximation na yan? Tama, Born-Oppenheimer approximation. Lastly, these are configurations of particles in a system that describes the exact position and momentum of each particle. Microstates. Very good, guys. Yay, and now we are done. Yan. So I hope, guys, na marami kang tutunan sa ating quantum mechanics crash course for today. Okay? Again, more on basics lang to. Now you're ready to answer practice test 1. So that is for 10 items and you can just answer it in 15 minutes. Okay? So guys, thank you again once again for